Hello. So, good evening. Welcome to the week 9 live section of the NPTL course Design of Reinforced Concrete Structures. I am Sanjay Kumawat, and today we will be having the live section on the design and analysis of columns. So, let's begin with it. So, let's first have a look at the types of column. So the types of column, they are mainly classified on various bases. So some of the classification basis I have displayed it over here, and the other one you can see it on your own. So this column classification, it is based upon the eccentric or the type of loading. So if we have a axial loading which is concentrically loaded column, then such a column it is called as axially loaded or concentrically loaded column. Now when we look at the eccentricity of the column, then in the eccentricity we can have two types of eccentricities in the column. That is, the first eccentricity can be either the column can be eccentrically loaded only on one side, that is, it is uniaxially loaded, and the other case can be the column is having eccentricity on both of its side. So to visualize this, I'm sorry. Okay, so to visualize this, I don't think you must be having any difficulty. So if the column is purely loaded axially, then we call it as concentrically applied load. And if the column, if it is loaded at some other point, for example if it is loaded at this point, then it will have some eccentricity E, and because of which this actually we will call it as uniaxially bended column. And in the second case, if we look at, if we have a load which is lying somewhere here, so we have eccentricity in both the direction, and that is the reason we will call it as column which is having biaxial eccentricity. So this was the classification of it, the columns based upon the loads. Now let's look at the classification of column based upon its slenderness ratio. So both of these classification will help us to identify how we should design our column. So in the first case, what we had is the type of load. In the second, we have the slenderness of the column. So based upon the slenderness of the column, we can classify it into the classify this column into these two types. That is, firstly the short column, and the second being the slender column. So the slenderness ratio is the one which helps us to decide whether the column is short or long. So slenderness ratio is nothing but the ratio of effective length to the radius of gyration, and the simplified version of this is nothing but effective length by least lateral dimension in case of columns. So a short, the more clearly we would be seeing how to identify this whether the column is short or slender in the next slide. But this is an important aspect which you should know, that the short columns, they predominantly go failure under compressive loads, or they will have a failure which is crushing failure. And slender columns, they usually see a failure in the form of buckling, which is an unstable form of failure. Now let's look at the other slides which shows us what is slenderness ratio. So slenderness ratio, which I already mentioned you, then we have, for different slenderness ratio, we have classified different structural components. So the firstly is the pedestal. So pedestal is a purely compressive member. There is no chance of eccentricity in this member. So a pedestal is a type, if you see it, you will visualize it like a block. So a block which is subjected to compression and which has a slenderness ratio less than 3, then we called it as what, pedestal. And if the slenderness ratio is goes if it goes above 3, then what we will classify it as column. Now under column we will have short column and long column. So short column, if the slenderness ratio is less than equal to 12 and greater than 3, then we will call it as short column. And about the long column, if we have a column which has slenderness ratio about 12, but the slenderness ratio, it should not exceed 60, or else it won't be possible to construct that. So because it will have a lot of bulging, because of which the column won't be able to sustain the load. So a long column would be a column which will have a slenderness ratio 12 limited to 60. Now slenderness ratio, as we have seen in the previous slide, it is the ratio of effective length divided by the least lateral dimension. Least lateral dimension is nothing but the dimension which is least in the case of column, that is B. And to calculate the effective length, what we will be doing, we will be having these two cases, that is columns in non-sway frames, and the other one is the columns in sway frames. So here I have classified these two forms, non-sway and in the sway frames. So in the non-sway frames you can see none of the ends can sway, as you can see in the three cases A, B and C. So in these three cases you can see that the supports which you are seeing here are in a form of fixed support, that is this end cannot move. So you can see here the first case is the hinged case, and in the hinged case we will having an effective length, or an effective length equal to the unsupported length. Firstly, I would also like you to know what is unsupported length. You must be knowing it. The unsupported length is nothing but the distance between the point of contraflexure, or the distance between the point of zero bending moment. So for the hinge case, we have the uh, effective length and the what we call it as the clear length has equal. So what we are saying, the ratio of this length to this length, it will be 1. And when we come to the fixed case, then the ratio of the unsupported length to the supported length will be equal to zero point 0.5. And when we broadly speak about the two ends which are partially supported, then the slenderness ratio, it would comes in between zero point 0.5 to 1. So slenderness ratio is what? It is the ratio of what it is? It is the ratio of supported length by unsupported length. Okay. Now now you should also keep this in your mind that for non-sway columns we have a slenderness ratio which lies in between zero point 0.5 to 1, and for the columns which are of sway type, for those columns we have slenderness ratio in between 1 to infinity. Now apart now the other factor which would also judge the design of columns are the minimum eccentricity and the load carrying capacity. So why to calculate the minimum eccentricity is because the in whatever precautions you take, however uh, uh, precisely you design or construct the columns, but there may be chances that the columns would have some eccentricity, and those eccentricity would be like accidental eccentricity, and it is very important to take into consideration the accidental eccentricity. So you can see it here, the minimum eccentricity formula which is given in IS 456, it is calculated as L effective by 500 plus D by 30 or the 20, a maximum of these two values. Okay. And for this case, if we have a minimum eccentricity, then the load carrying capacity of that column would be the load carried by the concrete plus the load carried by the steel. So from where this formula comes, you should be able to like guess it by now, because the compressive stress diagram which we have seen up to now in the beams, it was something like this. So this was the edge which was having 0.446 fck of stress. So whatever my gross area of column has, that I have multiplied it by the stress in the concrete, and what I have subtracted here is the amount of concrete which I have replaced it with the steel, and that steel, it is again multiplied by the steel in the concrete. So this is the way we calculate the ultimate load bearing capacity of columns. Now now again, important point we should know is this FSC would change depending upon the grade of steel. That is, for 250 it would be 0.87, for 415 and 500 it will be 0.79 and 0.75 respectively. Although sometimes we end up taking these two values as 0.75 FY only. Can Okay, we have only one guy here. So can you just tell me why we are having this reducing value of stress with increase in the grade of steel?
Can't remember, sir, exactly.
Can you guess? No guesses? Okay.
Yes, sir. It's due to the stress strain curve.
Yeah.
In the stress strain curve, where there is 0.2% proof stress, 0.002, that
Yes.
strain.
Yes. Exactly. So what is the point here is, the graph of Fe 250 is something like this, but when we look at the stress strain graph of Fe 415 and Fe 500, it will be something like this. So we are having some inelastic region before we are going into the yielding zone. So what happens when we look at the strain in the concrete? 0.002. Okay, I will discuss about this 0.002, why I am concentrating for columns to a strain of 0.002. But for the time being, just remember we will be having a strain of 0.002 in the concrete column. So for that strain, the stress which we have in Fe250, it will be corresponding to a yielding value of 0.87 Fy. But when we look at 0.002 value, okay, so this was the inclined line, but if you, even if you take the straight line, it will be having the same value. But this is not in the case of Fe415 and Fe500, because as soon as you bring this value here, what will happen? The strain, there is some mistake in the diagram. Actually, if you look, this 0.002 will lie in a region which is not exactly 0.87 Fy. So because of this non-linear region. Okay, so you can figure it out. Now, this was the minimum eccentricity criteria. Just remember these few things, it will be very important for you. For columns, what things you need to remember is how the column is loaded, whether it is concentrically loaded or eccentrically loaded. The second thing is you need to take care of the slenderness ratio. If the slenderness ratio is in between 3 to 12, then it will be a short column. If it is greater than 12, then it will be a long column. Afterwards, what you will check, you will check the eccentricity. If it lies in between these two values, then you will be having a load carrying capacity of this. And if the eccentricity, if it is less than 5% the lateral dimension, then the load carrying capacity, we will reduce it by zero point 0.9, or what, reduce it by zero point 0.9, or better I should say, we will reduce it by 10%. So here you can see the final load carrying capacity of a column which is less eccentric than the case which we have seen previously. So this is more eccentrically loaded column than this case. So the load carrying capacity has reduced, because the more the eccentricity, the more ductile behavior in the column we will be able to see, and the more ductility in the column, the more warning we will be getting. But as soon as the eccentricity reduces, the failure in the column would be judged by what? It will be judged mainly by the crushing failure of the concrete, which is very critical and it has no warning. That's why we are reducing the load carrying capacity of that column by 10%. So this was the reason behind this. And one more point I need to specify here is spirally or helically. I have not classified those columns based upon their lateral ties or based upon their shape. All those of things you can, like, you must be knowing that all already. So you must be knowing what is helically tied column. So if the lateral ties, if they are provided in the form of helicals in a circular columns, then we called it as spirally or helically reinforced column. So the load carrying capacity in case of spiral or helical column, we increase it by 5%. Why? Because this reinforcement, because of its continuity, it provide its additional confinement. So because of this additional confinement, the crushing behavior of concrete, it changes, or what should I say, it enhances. So this was about the eccentricity part. Now a few other guidelines that you that I have summarized over here for you. So the minimum cover in column, it should be 40 mm. This should be the minimum cover based upon the size. If the size is 200, then, or if the size is less than or equal to 200, then the minimum cover is 25 mm. Now coming to what, oh sorry, now coming to the minimum area of steel which should be present in the column. The minimum area, it should be 0.8% of the cross section area of column, and the maximum it should be 6%. But still we limit it to 4%. Why? Because in columns, because of this lapsing, we already cross, there are chances that we already cross the 4% or 6% criteria. That's why we limit it to 4%, so that even if there are lapsing in the column, we can have it in the range of 4 to 6%. Now talking about the transverse steel are the steel, this is the transverse steel, that is the lateral ties. And this lateral ties, they have a criteria for diameter, and they have a criteria for pitch. Pitch is the distance between these two ties. So we need to follow these guidelines. The diameter, it should be, the diameter of this lateral ties, it should be maximum of either 6 mm, or it should be one fourth of the diameter of the bars which is provided in the longitudinal direction. So this is longitudinal bar. Now when I talk about the pitch, this is the pitch. So pitch, it should be smaller of 16 times the diameter of longitudinal bar or 300. Now transfer steel for helical ties. This was for the lateral ties are usually provided in rectangular or square columns, but helical ties we can provide, or we can provide it only in circular columns. So diameter criteria would be same as the lateral ties one, but there is some difference in the pitch, and this comes up from a formula which I have not shown you here. So this pitch, it should not be greater than 75 mm. Pitch here in this case would be the this center to center distance between two spirals. So it should not be greater than 75 mm. It should not be greater than 1/6 of the diameter of that column. Then it should not be less than 25, and it should not be less than 3 times the diameter of that helical tie. So these are some additional guidelines that you should follow. Now let's look at one of the problem. So this is the problem. What it says: design the reinforcement in column of size 450 mm by 600 mm, subjected to an axial load of 2000 kilonewton under service dead and live load. Okay, so what it is saying, we are having an dead load, a combination of dead and live load is given, which is 2000 kilonewton. This is in service load. We will have to take care of the factor of safety, that is this service load has to be converted to design load first. Okay, now the column has an unsupported length of 3 meter and is braced against the side sway in both direction. Acha. So the column, it is braced in the sense it can be anything. It can be either fixed condition, or it can be hinged condition. Braced in the sense this, none of these two ends can move uh, relative to each other. So the other thing we have here is the concrete is M20 and the steel is Fe415, and we have a cover of 40 mm nominal cover. Okay, so let's begin with the design. So how we will start first? Firstly, you know the cross section. Then firstly you should see whether the column is short or not. So for that purpose, what will I do? I will calculate the slenderness ratio. So slenderness ratio is what? It is the ratio of least lateral dimension divided by, sorry, it is the ratio of effective length by least lateral dimension. So we don't know, they have only given us the column is braced, but we know for braced column the k, it lies between what, zero point 0.5 and 1. That is the reason I told you, for non-sway columns it is in between zero point 0.5 to 1, and for columns which can sway it is in between 1 to infinity. So you should take care of these terms. And slenderness ratio, as you know, it is L effective by least lateral dimension. So what we have here is, so these are the two quantities calculated in the two direction of the columns, because we have 450 and 600, the two lateral dimensions. Now since we know what we know, it will be lying in between zero point 0.5 to 1. So even if we take the least one, so this will be 2.5, and this will be something 3 something. So this is less than 12, so this is a short column. Okay, so this is the way you can judge without even knowing the support condition. So next, now our work is very easy. What we will be doing, we know this is a short column. Now what we will do, we will calculate the reinforcement, and before calculating the reinforcement we should know the load carrying capacity. For calculating the load carrying capacity, what should we know? We should know what is the eccentricity, whether it is within 5% of least lateral dimension or it is within the other criteria. So we will check both of the condition in both the direction. So this is in x direction and this is in y direction. So as you can see here, lx by 500, it comes out to be 26. So 26 is greater than 20, and that is the reason we are taking 26. And when we look at the strain in y direction, so this is also greater than 20. Now we are checking the 0.5d criteria. So this is coming out to be 30, and this is coming out to be 22.5. Okay, so our eccentricity is less than these values. So now what we will do, we will calculate the factored load or design load. Then, as you know, the formula for load carrying capacity of column would be this. Why we are taking zero point 0.4 and 0.67? Can you explain?
Due to the eccentricity condition, it is greater than 20 and
Yeah, because now
0.05.
because now the eccentricity is falling within the second criteria. Okay.
Yes, sir.
Okay. So we have the area of steel, and based upon the area of steel, I am taking 4 bars at the corners and 4 bars at the interior. So based upon this, I am calculating the area of steel which is provided, and from this I am calculating the percentage of steel provided, which is greater than zero point 0.8. So I have met the criteria. Now other design would be the tie diameter and the tie spacing. I'm not emphasizing on them. You can look at it by your own. So final would be the reinforcement detailing of this column would be like this. So we will be having this column with longitudinal bars and ties. So these ties are spaced alternatively. So this tie, if you look it in the plan, this is like this, and if you look this tie in the plan, then you will look, it will look something like this. So we have this ties alternatively placed. So this was about the concentrically loaded column. Now let's also look at a column which is not only subjected to load but also subjected to some eccentricity. So this is somewhat more interesting, and a lot of concepts I hope would be cleared from the you. Firstly, we will be discussing about the uniaxial bending in the column. So this is the uniaxial bending of the column part. So before proceeding, we should first see what all assumptions we have. So assumptions we have is the axial strain in the column, we assume it to be 0.002, and the maximum strain in concrete due to axial load and bending moment at the highly compressed edge shall be 0.0035 minus 0.75 epsilon. So don't worry, we will be I will try to explain you these assumptions as well as this strain diagram intuitively. So first of all, look at this. This line is what? This line is the lateral dimension of my column. Okay. So my since it is a column, so this upon this line, what I will be saying the compression strain. So if my column is purely actually loaded, so each and every point on this line would be having a strain of 0.002. This is my first assumption. Okay. So axial strain in my column is 0.002. Now let's look at a case where my column would be subjected to both compression as well as bending. So how will that case look like? So this was the case for pure axial compression. Now we will have a case where we will having both compression as well as tension. So what will happen? My strain diagram will go on shifting towards the tension side. So this is the compression side, and the above this line would be the tension side. So I will slowly shift the load on the column in such a way that my column will experience both tension as well as compression. So this will be the next. Okay, I will draw it separately. So suppose this is the first case, this is the second case. In the third case, what we'll have? We will have at one edge of the column the strain will be 0, while at the other edge it will be compressive. Now in the fourth case, we will have a case in which my column strain will something look like this. Okay. Now I will try to explain you this with the help of this diagram present over here. So just try to understand this. You all know when in beams, when we studied the stress diagram, it was looking something like this, and the strain corresponding to this stress diagram was something like this. So for the maximum stress, we what strain we had in concrete was 0.0035, and at the point of 3d by 7, my strain was 0.002. In the similar fashion in column also, what we assume the maximum strain in the column, it will go to 0.0035, and for this strain the corresponding tensile strain we will have to check, okay, in columns. Okay. So this is the uh, 0.002 line, and this is the line for 0.0035. So between, if my strain is in between these 2 points, so you can see this is purely 0.002. Now slowly my strain will shift here, and when I extend this line, what will happen? So this is the case 2. So this is the edge which is highly compressed edge, and this is the edge of the concrete which is less compressed. So what this second assumption says to us, the less compressed edge, the highly compressed edge will have a strain of 0.0035 minus 0.75 epsilon. Epsilon is the strain at the this point which is compressed less, this point. Okay. So you can easily, with the help of similarity of triangles, you can easily figure it out from where this 0.75 comes. I leave it to you. And as the compressive stress increases, it will reach to 0.35. And then when I draw this, sorry, and when I draw this, what will happen? See, my strain will again pass through this pivot point. This is the pivot point, that is the point of 3D by 7, as you can see it here. And further, my strain in the concrete won't go above 0.0035, but the tensile strain in the, okay, let me use some other color. Tensile strain in the concrete, it will in such a manner that at one side the strain will be tensile, and on the other side the strain will be, so in this way. So this is somewhat difficult to understand, just revise this, I suggest you. So if you see it here, at the pivot point we are having strains which are lying on the compression side, and some strains are lying on the tensile strain side. So for the first case, that is the case 1, for the case 1 where my strain along all points for 0.002, for that point my xu, that is this one, this we call it as xu now. My xu was in greater than d, or I can also say it that this xu could go infinity for this point, for green one. Xu was infinity because there is no point where we can say like at above this point we have compression and about this point we have tension, because there is no tension for green line. And for red line, my xu, it comes into picture, and slowly as we go toward the blue and violet line, we have a finite values of xu. Okay. So so this strain distribution diagram is important from the point, if you want to understand from where the uh, moment interaction curves for columns are derived. So if you understand this strain diagram, it would be very easy for you to understand the interaction or the derivations from where the interaction diagrams are derived. Okay. So I won't be taking the derivation by how the interaction diagrams are derived. So just to, okay, sorry for this. So just to make you all familiar about the strain diagrams from where the interaction diagram comes, I just showed you this strain distribution diagram. So now let's talk about the PM interaction curve. So forget everything. If you only want to design and analyze a column, you need to understand this PM interaction curve. So here we have a cross section. If the column is actually loaded, then what will we have? We will have only an axial load. But when the column is loaded eccentrically, then because of this eccentricity we will have some moment which will be having a magnitude of P into E. Okay. So let's quickly try to understand this PM interaction curve. This is very interesting, just pay attention. So we have an x-axis, on y-axis we have the load, and on x-axis we have the moment, which is equal to force into E. So just see what we are doing, because the column, it has to be designed for dual nature of loads. We are having this PM interaction diagram because we need to take care that the column is safe in both loading as well as in the moment. So to ensure the safety for both type of loads, we will have to see the PM interaction diagram. So on the y-axis we have the axial load, and on the x-axis we have the moment. And if we have a graph y x, y is equals to mx, what is m is the slope. Now what we have here is, we have m is equals to pe, or I should have written ep. So what is e is the slope. So what can I say? The slope of this PM interaction diagram, what will be, what we will get from that? What we,
Eccentricity.
eccentricity, yeah. So we will get eccentricity from the PM interaction curve. So this is also an important point. If any competition exam, they will ask you what is the eccentricity for this p and this m, and they will give you the slope values. You will get confused. So what is this? But this is as simple as that. You can see it here. Now another important point. First point was what? The slope. Slope is what? Slope will give me eccentricity. Second important point is, we have force on the y-axis and moment on the x-axis. Now see, on y-axis, the point number one, if you look at the point number one, any structure which has purely axial load, then the point number one will indicate a column with axial load, pure axial load. And as we go below this curve, that is at point number 1 dash, then the 1 dash is the point which corresponds to a structural component which will have axial load with some eccentricity. So better, I would like, let me classify it in this way. The point 1 is the point where we take the eccentricity to be less than 0.05 d. Okay, and here we have the load carrying capacity has zero point 0.4 fck plus 0.67, whatever it was. Now on 1 dash, this is the case for the eccentricity where we assume it to be L effective by 500 plus, what was that, I don't remember, d by 50, d by 30 I think. So for this point we were having p has 0.47 fck plus asc into fsc. Now leave point 2. When we come from 1 dash to 3 dash, 3 dash is the point where the cross section of the column will have zero strain at one point and maximum compressive at the other point. So beyond point 3, when we look at the structural column, beyond point 3, the column will start experiencing both compressive load as well as tensile load beyond point 3. And it will come to point 4. After point 4, what will happen? Point 4 is the 4 where the eccentricity will correspond to balance eccentricity. That is, both my steel as well as the concrete, both are having what? They are having same yielding. The yielding would be same. So beyond point 4, what will happen? Beyond point 4, my steel will yield more, or what can I say, the tension in the structure would be more as compared to the compression. Now I have a quick question for you again. When you look at point 4, you know above point 4, what I said at point 4, again from 1 to 3, from 1 to 3 in my graph, the load was purely compressive with some eccentricity. And when we come from 3 to 4, what I said the loads are both compressive plus tension. Okay, at 4, what I said, at 4 I have a load which is balanced load, and for that load I have both steel and concrete yielding at the same time. Okay, so up to 4, in between 3 to 4, my compression was dominant. At 4, both compression and tension are equal. And when we go on further from 4 to 5, my tension will be greater than compression. Here compression is greater than tension. So these are all the five cases, I think. Now I have a question. When you design this column, would you be suggesting me to design it at a point which is less than 4, or would you suggest me to design the column for a point which is greater than 4?
Sir, less than 4, because concrete is poor in tension.
Okay.
Buckling failure can happen
Yeah.
for points greater than 4.
Okay. So also you, at point 4, what I said, at point 4 steel and concrete they yield simultaneously, yes. And below point 4 concrete will yield first and steel will yield afterwards. Think in that way. After point 4, between 4 and 5, what will happen? Steel will yield before concrete. Are you getting me?
Yes, sir.
So now what you will suggest me?
Mm, sir, don't know, sir.
See see it is easy now. What happens? Be- Between point 3 to 4 my concrete is yielding first, so the failure in concrete will occur first, so I don't want that. So it is better to design in between 4 and 5. Okay. Now at point
Yes, sir.
5, what is the speciality of point 5?
Here, actually, I don't know much about
Yeah,
this.
I will explain you. So at point 5 p is 0.
Pure, pure means
Pure
what to say?
bending moment. Yeah.
Yeah, pure bending
So
moment.
what is the structural component? uh,
Beam.
Beam. Oh, so what can I say? I can say the y-axis of the PM interaction curve. The y-axis of the PM interaction curve, what it deals with? It deals with the design of purely axially loaded columns. Do you get me? And when we
Yes, sir.
look at the x-axis, since the eccentricity here it is infinity, we are having the stress resultant which are present on the x-axis are only the moments. So what can I say? So what will be the value of p for the x-axis?
For the x-axis value of
X.
okay, okay.
Yes.
P value. It will be in transverse direction. I
No,
don't.
no. Here you point for point 1 it was 0.46 fck. For point 1 dash it was 0.47 fck. What will be the value of phi? P.
Sir, I don't know.
Array, this is the on the x-axis we design it for beam 0.36 fck.
Okay.
See,
Uh,
for
yes,
beams,
sir.
what we
Yes.
take it for beams. So see, everything is linked. From column to
Yeah.
beam the PM interaction is so much linked. So from 1 to 5 we will having a nature mixed nature. On on y-axis we will having purely column, on x-axis we have purely beam. Okay, so did you get me?
Yes, sir.
So I tried my, I don't know, it is not my level best, but I tried to explain you intuitively how from column to beam this PM interaction curve it varies. Okay, now let's move
Yes, sir.
on to some charts. Okay, one more thing I want you to know. If this is the PM interaction curve, and any, suppose you have some force P and some moment M, and someone told you that like this and these are the dimensions of my column, and just check the column whether it is safe or not. So what you will do, you will just locate those P and M in the PM interaction curve. If for those P and M, if my the point for which, if it lies in inside the PM interaction curve, then it is safe. And and if the point, if it lies outside the PM interaction curve, then it is unsafe. Okay, so whatever uh, lines, so whatever points of P and M we have on this line, red line, those are the ultimate points. Beyond those points my structure will fail, below those points it is fine. Okay, so this was about the analysis part. Now let's look at the design part. So what if we want to design the a column which is having uniaxial loading? So We have some charts in SP16, special publication 16, those charts. So here also, quickly let me summarize this for how to look at these charts. Firstly, you have to look for fy value. Secondly, you have to look for d dash by d value. Thirdly, you have to look for arrangement of bars. Okay, so based upon your problem, first see what fy value you are looking for, then you see what is d dash by d. D dash is nothing but nominal cover by least lateral dimension. Based upon this, select your chart. Then third criteria, you will be seeing whether my uh, column is uniaxially, it is having uniaxial bending or biaxial bending. So if it is having uniaxial bending, then it will have bars on only one side. Again, uniaxial columns can also have bars on all the four sides. Why? I will discuss it in one of the problems. So this was about this chart for uniaxial. Remember these three things, it will be very useful. Now, what if I want an arrangement of bars in all of the four direction? So there are some other criterias. So to have the bars, here I am pointing out, if to have the bars in all of the four direction, this is some of the guideline. Firstly, you should be taking care that at least 30% of the, at least 0.3% or 30% of the bar, of the reinforcement bars, it should be provided at the edges, outer rows. So these are the outer rows, and the remaining you can provide it in the inner rows. So these are the inner rows, these are inner rows, and these are the outer rows. Okay, so this you have to take care. Now let's look at this problem. So what the problem says, just a second. Okay, so what the problem says, a rectangular short column has section dimensions 300 mm by 600 mm. It is subjected to factored axial load of 1400 kilonewton and a factored moment of 280 kilonewton meter about the major axis. Okay, so they have already given me the factored axial moment, so no need to multiply it by some factor of safety because P and M both are factored. So from this also you can understand why they will give us M, because they want us to design it as a column which is subjecting to moment as well as load. Now design the column using M20 and Fe415. Effective cover is 60. So let's begin with the design. Firstly, what will I have to do? I will have to check Fy. Okay, it is 415. Now what I will have to do? I will have to check D dash by D. Okay, see D dash by D, I can check it. Now D dash by D, what is it? Just quickly tell me. 60 by 600. So it is zero point 0.1. So this two, from this two I can select the chart. Third criteria is to know the arrangement of bars. So what type of bars arrangement will you suggest me? Whether you will suggest me this type of arrangement or this, for this problem.
The above one, because it's 280 kilonewton about the major axis.
Okay.
One direction uniaxial.
Yeah, it's fine. I told you, since it is axial loading, I can go for this one. But there are some cases where I will have to go for this case also, even if it is uniaxial. Why? Do you know the minimum spacing criteria between two bars? How much it is? Maximum spacing, sorry. What should be the maximum spacing between two bars?
Uh, 75 or 300 something was,
300.
I
Okay.
don't.
75 is for ties, and for bars in longitudinal direction, the 300 should be maximum. But this is the major sorry, let me first erase this columns. This is a very interesting and a very widely asked topic, so just try to understand this. So suppose this is 600 and this is 300. So since I will be having bending along this axis, so my bars will be like this. Am I correct? No, I am wrong. My bending will be along this axis, because major axis is the one which has higher moment of inertia. Higher moment of inertia will be 300 into 600 cube by 12. So this should be the depth. So the higher the direction in which the depth is higher, we expect the beam to bend along that direction. Okay, so these are wrong. So since bending will take along this axis, like the moment will act like this. Let me clear first. So the moment will act like this. My it will bend. The column will bend along this axis. So this will be 600, and my bars will be placed like this along the direction where the bending will take place. So now the if I provide only bars in along the outer rows, what will happen? Since this is only 60, 600 minus 120 is 580, no, 480. It is 480, which is greater than 300. So minimum spacing criteria we are not able to follow with this type of arrangement. So we will have to go for this arrangement. So look for a chart in SP16 which has Fi as 415, D dash by D as zero point 0.1, and the third case is for arrangements which has both outer rows and inner rows. So whatever I just discussed in this part, this is only mentioned here in this. Let's move on further. So I know I have selected the chart. How will I determine the area of steel? Okay, so I would also like you to first know how to read this chart. See here, how to select the chart, that is fine, but how to read this chart? We have two axes, y axis and the x axis. Both the axes are having normalized axial load and normalized moment. So axial load is normalized by pu fck bd, and moment is normalized by fck bd square. So based upon these two values, I will like just see where these 2 points meet, and these are the different curves upon which the different percentage of steel is mentioned. Okay, the percentage of steel, it is mentioned in the form of pt by fck. So just by multiplying by fck you can get the pt. So in this manner I have calculated the d dash by d. Then I have the normalized pu value, I have the normalized mv value. Now I will look into this chart for this three. I am getting p by fck. You can see here I have shown it, this line. So it meets here. So this points corresponds to a p by fck. P is nothing but the percentage of steel, 0 point. See, once you understand, the designing part is very easy. You will get percentage of steel. Now calculate the area of steel. Area of steel will be simply b into d. Then once you see, this was a problem in which designing was in terms of only the reinforcement. There are designs in which you will also have to decide the dimensions. You are lucky that the dimensions are already given in this problem. So we will be also seeing some problems in which the complete designs of a column will be covered. Okay, so as I told you, at least 30% of the bars should be present in the outer row. So the 30% of the bars I am providing it in the outer row, then the remaining I will be provided in it in the inner row. So also you can see this, the uh, criteria for the transverse reinforcement. So this is the final design. So as you can see, 600 and 300 are my cross section. Then I have two rows of bars in the outer edge and two rows of bars in the inner edge. And what I have what I have is I have ties. So these are the ties. Why I have internal ties? Because there is one more clause in IS 456. If the distance between two ties, if it exceeds 75 mm, then I will have to provide ties in between also, and that is the reason. So this distance is greater than 75 mm. That's why we have more number of ties. So this was all about the design of uniaxial and the uh, short columns in this live sessions. In the next live sessions, I will be bringing up with more design based problems which would be dealing with both axial as well as biaxial as well as uniaxial bending in the column, and the biaxial pm interaction curve, that would I will be also explaining that. And it is also an important concept to learn and to have an idea of the design. So this was all about this class. If you want to ask me anything, the floor is open for you.
No, sir, I don't have any question right now.
Yeah, it seems like you are not very comfortable with columns.
Yes, sir, I have to work on them.
Yeah, but you have seen the concepts of PM interaction, how interesting it is. You can from column to a component which is subjected to both compression and eccentricity, and then finally we have the beam on an x-axis. But
No, sir, actually, I have to work more on
yeah,
them.
yeah, but from
I,
today's lecture you have like realized, na, from this PM
yes,
interaction,
sir.
you must
Yes,
have
sir.
realized this one.
Yes, sir.
Okay, if you don't have any question, I would like to conclude this live session, and we will meet in the next class on next Tuesday from 6 to 7. Thank you.
Welcome, sir. Thank you, sir.
Okay, bye.
Bye, sir.